The rational numbers are dense, ordered, and algebraically excellent, but a bounded rational set can still lose its supremum. We will construct real numbers as Dedekind cuts, carefully selected lower subsets of the rational numbers. Then we will define addition and multiplication, state the omitted ordered fieldwork, and prove the least upper bound property completely. Last time, the positive rationals with square below 2 had no rational least upper bound. Dedekind's idea is to describe a boundary by recording every rational number strictly below it. We do not first assume the boundary exists somewhere else. The lower set itself becomes the new number. We have replaced one number with infinitely many rationals. Correct. Infinity has finally received administrative duties. A Dedekind cut is a subset A of the rational numbers satisfying three conditions. First, A is non-empty but not all of the rational numbers. A boundary must leave something on both sides. Second, A is downward closed. If X belongs to A and Y is smaller than X, then Y also belongs to A. Third, A has no greatest element. Above every X in A, another element of A still remains. Define the real numbers to be the collection of all Dedekind cuts. Each real number is literally one of these rational subsets. For each rational R, define R hat to be the set of all rational Q strictly less than R. It is non-empty because R-1 belongs to it, and proper because R itself does not. It is downward closed, and if Q is below R, the midpoint of Q and R lies strictly between them. Thus there is no greatest element. So every rational produces a real cut. We identify 0 and 1 with 0 hat and 1 hat, and embed R by sending it to R hat. Define D sub 2 using all negative rationals and all rationals whose square is below 2. 0 belongs to D sub 2, while 2 does not. If Y is below X in the cut, negative Y is automatic. Otherwise Y squared is below X squared. If X is non-positive, increase it to 1. If X is positive, the displayed rational correction T gives a larger point still inside the cut. Therefore D sub 2 is a Dedekind cut. It is a real number by construction, but it is not R hat for any rational R. Define A less than or equal to B when A is contained in B, and strict inequality when the containment is proper. For rational cuts, R is less than S exactly when R hat is properly contained in S hat. The old rational order is preserved. Any two Dedekind cuts are comparable by inclusion. This follows from downward closure, although the verification still has to be written. For cuts A and B, define A plus B to contain every rational sum A plus B with A and B in B. For embedded rationals, R hat plus S hat equals the cut at R plus S. So this operation extends ordinary rational addition. A formula between sets is not automatically an operation on real numbers. We must prove its output is again a Dedekind cut. Non-emptiness is immediate. Choose A and B in B, then A plus B belongs to the sum. For properness, choose alpha outside A and beta outside B. Then every A in A is below alpha and every B in B is below beta. Therefore every A plus B is below alpha plus beta, so alpha plus beta does not belong to A plus B. If Y is below A plus B, then Y minus B is below A and belongs to A. Hence Y equals Y minus B plus B, and lies in the sum. Finally, increase A to some A prime still in A. Then A prime plus B is a larger element of the sum. All four cut conditions hold. So addition really maps two real numbers to a real number. The definition has survived its background check. The real 0 and 1 are the rational cuts 0 hat and 1 hat. Define negative A to contain every rational Q lying strictly below negative R for some rational R outside A. The strict inequality removes any accidental endpoint, because a Dedekind cut is not permitted to have a greatest element. One must prove negative A is a cut. The negative of R hat is the cut at negative R, and A plus negative A equals real 0. Those verifications are routine but not optional. We record the definition now because multiplication needs signs. Assume first that cuts A and B are non-negative, meaning each contains the real 0 cut. Define A circle times B to contain every negative rational, together with every product AB formed from non-negative A and B and B. The negative rationals are included automatically because every cut representing a non-negative real must contain them. Using only non-negative factors avoids the order reversal caused by negative rational factors. The product is non-empty because it contains every negative rational. Choose positive rationals alpha outside A and beta outside B. Every non-negative A and B satisfies AB below alpha beta. Thus alpha beta is outside the product, proving properness. For downward closure, negative Y is automatic. If 0 is at most Y below AB, then A and B are positive and Y equals A times Y over A. Since Y over A is below B, downward closure of B puts that factor in B. So Y belongs to the product. Every negative member can be increased toward 0. A positive product can be increased by increasing one positive factor. If 0 lies in the product, both cuts contain non-negative members. Their no greatest property supplies positive ones and a larger product. If either factor is the 0 cut, 0 is not in the product, and the product is exactly the 0 cut. Therefore the non-negative product is again a Dedekind cut. Define the absolute value of A to be A when A is non-negative, and negative A when A is negative. If both cuts are non-negative or both are negative, define their product as the non-negative product of their absolute values. If one cut is non-negative and the other negative, take the additive negative. 0 times a negative cut remains 0. With this definition, R hat times S hat equals the cut at R times S. Proving this still requires sign-by-sign algebra. These definitions do not make the ordered field laws true by topography. Each law requires a proof from the cut definitions. One must prove the additive and multiplicative laws, construct reciprocals for non-zero cuts, and verify distributivity. One must also prove inclusion is a linear order compatible with addition and with products of positive cuts. We omit those lengthy standard arguments. The precise result is an ordered field containing an ordered copy of Q. Our remaining task is the property that motivated the construction, completeness. Let E be any non-empty collection of real numbers that is bounded above. Its elements are cuts, because the real order is inclusion. Bounded above means there is a cut U containing every A and E. We must construct a cut that is an upper bound of E and is contained in every other upper bound. Define L to be the union of all cuts A and E. A rational X belongs to L exactly when X belongs to at least one cut in the family. Every A and E is automatically contained in L, so the union is already the natural upper bound candidate. First prove L is a real number. An arbitrary union of cuts could equal all of Q. Boundedness prevents that enthusiasm. Because E is non-empty, choose a cut A sub 0 in E. Since that cut is non-empty, any one of its members belongs to L. Because U contains every A and E, their union L is contained in U. Since U is a proper rational subset, L is also proper. If X belongs to L, then X belongs to some A and E. For y below x, downward closure of A places y in A and therefore in L. For the same x in A, the cut A supplies z in A with x below z. Then z also belongs to L. So L has no greatest element. The union is non-empty, proper, downward closed, and has no greatest element. Hence L is a Dedekind cut and therefore a real number. For every A in E, the definition of union gives A contained in L. Under the inclusion order, A is at most L. Therefore L is an upper bound of E. Now let V be any upper bound of E, then every A in E is contained in V. Taking the union preserves that containment. So L is contained in V. Thus L is at most every upper bound. Consequently L is the least upper bound of E. Embed every Q from the P15 set S as the real cut Q hat, producing a bounded family E sub 2 of real numbers. Its real supremum is the union of those rational cuts, and that union is exactly D sub 2. If X lies in the union, then X is below some Q in S. Thus X is negative, or X squared is below Q squared and therefore below 2. Conversely, for X in D sub 2, use Q equal to 1 when X is nonpositive, and Q equal to T of X when X is positive. Then X is below Q in S. No rational R hat equals D sub 2. But D sub 2 is a real number. The missing boundary now lies inside the system. A real number is a non-empty proper lower subset of Q with no greatest element, ordered by inclusion. Addition uses pairwise rational sums. Multiplication uses non-negative products first. Then additive negation handles the signs. The ordered field laws all require proofs from these definitions. Their omission is bookkeeping, not divine intervention. For every non-empty bounded family of cuts, its union is a cut and is exactly its least upper bound. Therefore the Dedekind cut real numbers form a complete ordered field containing the rational numbers.